Nirmal, once your friends came into the meeting, then please remind me. Okay. Um, we will refresh the things which we have discussed in our Lagrange interpolation. Uh, Okay, this is what we have seen in the last class. Lagrange interpolation, triangular family, numerical differentiation, integration. This is what we have to discuss. This is the left syllabus in our numerical methods, and Lagrange interpolation formula for unequal intervals. This is what we have seen in the last class. We'll refresh these information once Nirmal team came into the picture. Then we'll hand over the session to Nirmal's team. And see, this is f of x naught and f of x1 and so on, f of xn be the value of the function of y corresponding to the arguments x naught, x1 and so on, xn. And this is not necessarily equally spaced. And let f of x be the polynomial in x of degree n. Then we can represent f of x as a naught into x minus x1 and x into a naught into x minus x1, x minus x2 and so on, x minus xn plus an into x naught, x minus x naught, x minus x2 and so on, x minus xn plus and so on plus an into x minus x naught, x minus x1 and so on, x minus xn minus 1. Let this may be equation number 1. And the things which we have to remember is the term when we have the coefficient a naught, in that the term we doesn't have x minus x naught term. When we have the coefficient a1, then we don't have the term x minus x1. Similarly, and so on, when we have the coefficient called an, then we don't have the term called x minus xn. Therefore, we need to remember what is f of x, and where the coefficients are constants. And now we can determine the constants, that is applying x is equal to x naught in 1, we will get the constant a naught, f of x naught divided by the coefficient which is associated with all the terms. When we are applying x is equal to x naught, what it happens, the other terms which is apart from a naught becomes 0, because the terms we have x minus x naught in all the other terms. Therefore that becomes 0. Therefore we will get only the term which is associated with a naught. Therefore, and a naught is equal to f of x naught divided by x naught minus x1, x naught minus x2 and so on, x naught minus xn. This is let this equation be about equation number 2. And similarly for f of x1, and similarly for an. And by applying these equation number 1, we will get, this is the equation which is necessary to solve the Lagrange interpolation formula. This is what we have discussed in the last class. And now we can hand over the session to Nirmal's team. Nirmal?
Yes, sir, we are ready, sir.
Yes, go ahead with your presentation.
Yeah, good afternoon, everyone. All. Am I audible?
It's little louder.
Am I audible? Sir, now?
Yes, Chitesh. Chitesh.
Okay, sir.
Okay, good.
Today we are going to see the effect of non-linearity on Taylor series. Uh, just a minute. So now let us take the function y equal to x power m.
Chitesh, just a minute. Chitesh, what was your last class, Chitesh?
So Taylor series,
No, 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 no. Last hour. Till
MM is
30.
metallurgy and materials.
Why? In that class also you have very less attendance. Only concerning to our class, so far we have so far 23 people only, 22 people only joined, and
Yes, sir. In the beginning, it will be like this. Most classes, it will be like this only.
hope the others will join. Okay, you take the decision.
Now, shall I continue, sir?
Yes, yes.
Yeah. Now we let us take the function y equal to x power m, uh, uh, where m where m indicates 1, 2, 3, 4, etc. Some that etc. Now we can see that when x equal to 1, y will for all values of m, y value will be 1. So let us take x naught as 1 and y naught as 1. So now Taylor series approximation, the formula will become y of x1 equal to y naught plus m x naught x naught power m minus 1 into x1 minus x naught. So uh, y naught will be 1, so substitute them, and and x naught also will be 1. Next slide please. Hello. Yeah. uh, Now we can see x naught, when we substitute x naught equal to 1, the formula will become 1 plus m into x1 minus 1. So the difference, we can see the difference will be the balance part of the Taylor series. So that is written there lastly. So we can see that it depends directly on m. Next slide. Yeah, we assumed function y equal to x power m. So for different values of m, the uh, between y values between 1 and 2 is depicted in the graph, and we can see the nonlinearity increases as m increases. For m equal to 1, it is a straight line, it is linear function, and for m equal to 2, y equal to the function is y equal to x square, so it becomes nonlinear, and as m increases, the function becomes more nonlinear. So we can see so the we in the previous slide we saw that um, the error depends on m. So as non-linearity increases, the error increases. This is what we conclude. And next slide. Yeah. In this table, yeah, I have depicted the values and approximation for y equal to x. F of 2 will be uh, 2. So f of 2 will be 2 power 1. So 2. And the approximation will also result in 2. So the error will be 0. And as m increases, the difference increases to 1, 4, 11, and 26. So we can clearly conclude that as nonlinearity increases, the error increases and the approximation becomes more deflected from the original value. This is the effect of nonlinearity in Taylor series approximation. And in all of our approximation, we have taken only linear approximations. For just for one term we have taken. Okay, next slide. Yeah, now we shall see the effect of step size in the approximation. The step size is nothing but the difference, difference between x1 and x0. So the if we substitute that h equal to x1 minus x0 in the formula, the linear approximation, we can see y1 equal to y0 plus m into x0 power m minus 1 into h. So the difference will be the remaining part of the Taylor series. That is, the error will be the remaining part of the Taylor series. We can see from the formula that error depends directly on h square for small values of h. So the difference increases as h value increases. So the error will increase as as the step size increases. So we can conclude that the Taylor series approximation, linear approximation, becomes poor as the step size is more. Next slide. Next slide, please. Yeah, here we have taken the function f of x equal to x power 4. And for h equal and taken different values of h. So for h equal to 1, x0 is we have taken 1. So x1 will become, if h is 1, x1 will be 2. So 2 power 4, 16. So the true value is 16. And the first order approximation is x0 uh, is 1 plus 1 plus m will be 4 into again 1. So 1 plus 4 into 1, 5. So the first order approximation is 5. And R1 is nothing but the error. So the difference is, here we can see 11. So similarly, if h increase h, if we reduce the value of h and find the values, so we can see the error decreases as h decreases. So this is this is first order approximation, and from this we conclude that we can clearly see from the table. So as the h value is decreases, the error value also decreases. Okay, next slide. Now we take y equal to x square. The function, now we take the function y equal to x square, and y naught will equal to 1, x not equal to 1, and try to find y of 9. So we can see the true value will be x1 is 9. So the true value will be 9 square, 81. Now we try to find y of 9 with different step sizes. Next slide. Yeah, here see, we have taken step size as 8, and we are trying to find y of 9 directly. So now we apply in the formula, and we can see y naught will be 1, and m is 2, as the function is x square, and x naught 1, and into h is 8. So 1 plus 2 into 8, y1 from the approximation we can find as it as 17. So the difference, the real value is 81, but what we found is 17. This is by taking the step size as h equal to 8. Next slide. Yeah, here the difference we can find 81 minus 17 is 64. Now we take the step size as 4 and try to find y of 5, and then we are going to find y of 9 with y5. So y of 5 we can find 9, and substituting y of 5 in Taylor series, we can find y of 9 as 49. So with step size as h equal to 4, the difference is 81 minus 49, it is 32. We can see the difference reduced by 2 when the different when we decrease the step size by 2, so the difference also reduced by 2. But initially we saw that the steps error is directly proportional to h square, but here it has decreased only by 2 because the number of steps we used to find also increased. So uh, from 64 it reduced to only to 32. Next slide. Now we take the step size as 2 and try to find y of 9. So first we are finding y of 3, 1 plus 2 into x naught we have taken as 1. So 1 power anything 1 into 2. So y1 will y of 3 will be 5, and with the x2 equal to 5 and try next we are finding y of 5. So now we can find the y of 5 value is 17. Next slide. From y of 5 we are going to find y of 7, and uh, substituting the values in formula, we can see the y of 7 is 37, and then again we are substituting the y of 7 value in the formula and using and finding y of 9. So we can find the value became 65 for by this approximation for step size h equal to 2. Now the difference became 16. For y equal to 4, for h step size equal to 4, we found the difference is 32, and for step size equal to 8, we found the difference is 64. Now also the difference reduced by 2 times. So we can say we can find the step size. The approximation becomes the error becomes the error is directly proportional to step size. That's what we conclude with this. And next slide. Yeah, this is the summary again. Everything in one slide. And next slide. Yeah, this in this diagram I have simply tried. This has no meaning, but I have tried to show you by some drawing. So first, the actual f of x is the semicircle, but when h step size h equal to 8, we are finding by the straight line. And in the second diagram, we can see taking step size h equal to 4, the straight line became more similar to the semicircle. Two straight lines are there, and in the third diagram, four straight lines are there, and it became more and more similar to the semicircle. And this is just my own drawing to depict, and that's all. From this session, we conclude that the non-linearity increases, the approximation becomes how to say, the error becomes error also increases as the non-linearity increases, and with the step size also error increases. That's all, and Nirmal will continue from this. Thank you.
Priti, next slide. Good afternoon, everyone. I am Nirmal and I am here to present the topic error propagation. First of all, let us know what is error propagation. consider two numbers with errors. If these numbers are substituted into a function, it is obvious that the function also has some error. Therefore, the process of finding the error that function has is called as error propagation. That is what I also typed in the presentation. If numbers with error are put in a function, the result also has some error in itself. The process of finding this error is called propagation. Uh, the purpose of propagation is to study how errors in numbers can propagate through the mathematical functions. Now let us understand this with an example. For example, consider two numbers, take x and y, which has some error in it. If these both numbers are multiple, that is multiplied, that is xy, it is a function. Xy also has some error. We will be excited to see what is the error in xy, so we need to learn how to propagate through functions. Next slide, Prithvi. Let us see functions of a single variable. Suppose that we have a function f of x that is dependent on a single independent variable x. Assume that x bar is an approximation of x. We therefore would like to assess the effect of discrepancy between x and x bar on the value of the function. That is, we would like to estimate the approximation of the function, that is delta f of x bar, that is equal to mod of f of x minus f of x bar. Next slide. We can approximate, but the problem in that is we didn't know what is x, so we need to use some formula to calculate the delta f of x bar. We know that we know the question will be given x bar. We know that x bar and x are close. uh, X bar is close to x. So by using Taylor series formula, that is f of xi plus 1 is equal to f of xi plus f dash of xi multiplied by f of xi plus 1 minus xi. Continued. We can use this formula to calculate delta f of x bar. That is, we can find f of x. Since x and x bar are near, we can using the above formula, we can write f of x as f of x bar plus f dash of x bar into x minus x bar. That is, we are substituting x at the place of xi plus 1 and x bar at the place of xi, since they are near to one another. Next slide. Uh, s- uh, since this function is only restricted to first order, we can omit the second and higher order terms, because the value of those terms are very negligible, so we can drop those higher order terms. After dropping those higher order terms, the equation becomes f of x minus f of x bar is approximately equal to f dash of x bar into x minus x bar. Um, f of x minus f of x bar is nothing but delta f of x bar, that is approximation of the function, that is equal to mod of f dash of x bar into approximation of x, that is x minus x bar. Next slide. And what I said is given in this slide again, where a delta f of x bar represents the approximation of the function, and delta x bar represents the approximation of x itself. So by simply using the above formula, we can calculate what is the error propagating through the function. The problems are very simple in this error propagation. Let us see a example problem. Give value of x bar is given as 2.5 and the approximation of x is given as 0.01. We need to estimate the resulting error in the function f of x equal to x cube. Next slide. By using that formula, delta f of x bar is equal to f dash of x bar. F of x is x cube and f dash of x is 3x square. F dash of x bar is 3 into x bar whole square. X bar is given as 2.5, so 3 into 2.5 the whole square into approximation of that is delta x bar, approximation of x, that is given as 0.01. Solving it, we get 0.1875. But we know that f of x, that is f of x bar, that is f of 2.5 is, that is 2.5 the whole cube, that is 15.625. Delta f of x bar is f of x minus f of x bar. Now we can find f of x, that is f of 2.5 is equal to 15.625 plus or minus the approximation, that is delta f of x bar, 15.625 plus or minus 0.185. Simply solving that, we get 15.4375 and 15.8125. That is the error of the function lies between these two. We can find whether what we have calculated using this formula is right or wrong by simply substituting the extreme values into the function. Since the approximation of x is given as 0.01 and the x bar is given as 2.5, simply subtract and add 0.01 to 2.5. We get 2.49 and 2.51. 2.49 the, now putting 2.49 into the function, that is x cube. 2.49 the whole cube is equal to 15.4382, and 2.51 the whole cube is 15.8132. We can note that the values of two extreme values, that is 2.49 and 2.51, are close enough to what we have found. So if we since we dropped the higher order terms, we see some difference in the values what we have got, but but getting such close values itself is enough. That is this is the method for error propagation. Thank you. Now Pradeep will continue.
Pradeep, what happened? Go ahead with your presentation. We are unable to hear your voice. Prithvi, Nirmal, what happened to Pradeep?
I am checking, sir. Wait.
Sir, am I audible now? Sir? So, I'm here to, hello everyone, I'm Pradeep. I'm here to continue with the graphical depiction of first order error propagation. And we are now presented with a simple graph between f of x and x. So the curve represents the function f of x, and in x-axis we plotted x bar and x, and the difference between them is del x bar. So now we are going to draw tangent at x bar with on the curve f of x. and we are going to project the 2 points x and x bar on the tangent line, whose projection on y-axis will give the estimated error, and with
Pradeep, you are using your cell phone or your laptop, Pradeep?
laptop, sir.
Please fast-check the settings of the mic. No, it is okay.
Opens
There is noise while sending. There's diffuse noise with your audio.
Shall I continue, sir?
Now it is okay. You continue.
Hello everyone, I'm here to continue with the graphical depiction of first order error propagation. So now we are presented with a graph between f of x and x, and we plotted x bar and x at x-axis, and the curve represents the function f of x. Now we are going to draw a tangent at the point x dash, and we are going to project x dash and x at the tangent line, and whose projection on y-axis will give the estimated error, and the same projection with respect to the curve will give the true error, and we can able to see the estimated error and true error which we calculated in the previous problems. So estimated error f dash of x dash into del x dash is the estimated error which we calculated in the previous problem. So next slide please. Next slide please. Now we are going to do the same thing for more than one variable condition. So we have to generalize the function for the function which are dependent on more than one variable. To accomplish this, we have to look for the multivariable version of the Taylor series. So for example, if you have two independent variables u and y, the Taylor series can be written as the following thing. So f of u I plus 1 comma b of I plus 1. The same thing f of u I bi. So in the formula we are going to drop all the second order terms because its value is going to be negligible. So we are given with the formula of del f of u dash p dash is equal to partial derivative of u with respect to f of x with respect to u into del of u dash plus partial derivative of f of f with respect to u into del v dash. So only difference is that we are going to handle the partial derivation in this condition than previous one. So next slide please. So we are going to generalize the same thing for more than two variables. For example, x1 dash, x2 dash, and x3 dash. So the change in value of x will be del x1 dash, del x2 dash, and del xn up to n terms. We are generalizing it, and in all the cases we are dropping the above second order terms. So which will do this, which will give us a result similar to So del of x1 dash partial derivative terms, partial derivative of f with respect to x1, like that it will go up to n terms. So next slide please. Now we are going to look on total numerical error. So we have seen termination error previous problems. That means when a problem is continued with a lot of steps. So if you are terminating a problem with particular some portion of steps, it will result in some termination error. And round off error is something which will be happen when we round off the answer in digits. So to minimize the round off error is to increase the number of significant figures of the computer. So termination error can be reduced by decreasing the step size. However, the termination error errors are decreased as the round off errors are increased. So in actual cases, it's relatively uncommon because computer and calculator devices will actually calculate how much term it has to round off and like that. Next slide please. We have seen that we have given the graph of that thing. So as termination error step size increases, the termination error will increase, but at the same time, the step size increases, round off error will decrease. So in order to maintain that both the thing at a point, we have to point of deviation returns. At that point, the total error will be very less. Next slide, please. So blunders are also known as a gross error. Could attribute to human imperfection, like while calculating we may miss something like that. So it occurs in computer programs. Also can occur in any stage of mathematical modeling. Blunders are usually disregarded in discussion of numerical methods. So next, formulation error. Formulation error, also known as model error, related to incomplete mathematical models. So incomplete mathematical model, in the sense it doesn't deal with other effects involving the calculation, like example is given. A negligible formulation error in fact is the fact that Newton's second law does not account for relativistic problem. This slide, please. And also data uncertainty. So errors sometimes enter into analysis because of uncertainty in the physical data. So uncertainty in the physical data is in the sense that when we have to depend on solution for data which we are providing, but when there is an error in the data which we are providing, means that's related to uncertainty. For example, if a parachute is falling from the height and is has to depend on its velocity sensor to estimate the velocity, but that may be uncertainty due to drag of air or change in atmospheric pressure, like that. So the data may not be valid like that. So from that I am done with it, and as Priti will continue.
Hello guys, till now my group mates explained all about the error propagations, and now you have already learned the formula for multivariable error propagation, and I'm here to give two last examples on it. This is nothing but something we have already learned during our JEE mains preparations. We have already seen problems of these types. This is just the application of Taylor series for the problem. So this is the question. A student makes the following measurements. Let's say A is 5 with an error of plus or minus 1 centimeter, and B is another quantity with 18 centimeter and plus or minus 2 centimeter errors, and C is 12 plus or minus 1 centimeter. T, the time is 3.0 plus 0.5 seconds, and meter M is equal to 18 plus or minus 1 gram. And then the question is to compute the quantity MB by T with its uncertainties and percentage uncertainties. So for this, we are going to apply the formula that we have already derived. This is it. F is equal to MB by T. MB by T is the thing we have to calculate, and then the error in the function, the total error in the function, can be given as delta F is equal to delta F by delta M into delta M. That is the partial differentiative of delta M. Plus delta F by delta B mod of delta F by delta B into delta B plus delta F by delta T into delta T. That is partial differentiation of the function with respect to all the three variables. And then we don't have to put minus sign here and all, because we only have to calculate the error, and that should be the maximum here. So no minus comes here. And then putting the values for it, partial differentiation of F with respect to M gives B by T. That's it, B by T here, B by T into delta M plus M by T mod M by T into delta B plus minus of mod of minus MB by T square into delta T. So that's here, and then we substitute the values given, that is 18, 3, 1 and 2 for all those. Calculating it gives us 30 centimeter per gram seconds. We can approximate it as 40 here, because we are just approximating the error here. And then the total function value is MB by T, that is substituting the given values in the function itself. It gives us 18 into 18 by 3, that is 108 centimeter. That is approximated to 110 centimeter to gram seconds. And then the percentage uncertainty we have calculated here as 40, that is the error value by the total value into 100%, that is 36%, that is 40%. So we have just given the approximate errors here. So the total function error can be given as 110 plus or minus 40 centimeter gram second. So that's one problem here. And then this is another problem. The deflection y of the top of a sailboat mast is given as y is equal to f into L power 4 by 8 into EI, where F is the uniform side loading, that is kind of pressure here. L is the height of the mast, E is the modulus of elasticity, and I is the moment of inertia. They are given the values for the force, length, what's it? A modulus of elasticity and the moment of inertia, and then the error values are given here. So applying the Taylor series formula, we can see that the partial differentiation leads us to dou y by dou f mod of dou y by dou f into delta f plus dou y by dou l into delta l, and all these things as given here. And then substituting the partial differentiation values, we get it as L power 4 by 8 into EI delta f plus FL cube by 2 EI delta L plus FL power 4 by 8 E square I into delta E plus FL power 4 by 8 EI square delta I. So that's the partial differentiation. And then substituting the values gives us this value, that is y is equal to delta y is equal to 0.011482. So the total error of the function is calculated here. Therefore, we can say that y is equal to 0.164025. That is the values which we get by substituting in the function itself, plus the error value as 0.011482. We can also say that y is between the extremes, that is plus this value and minus this value, that is 0.152543 and 0.175507. And then calculating the minimum and maximum values, we get this. So that's it. That's the presentation. So from today's explanations, what you have to take away is that Taylor series is very efficient to calculate errors in linear functions. It is not so much efficient and gives rise to errors in non-linear functions. And then we have to keep the step size as low as possible while calculating the errors in Taylor series method. So that's it. Thank you.
Yes, it was a nice presentation. Go, stay with the slides, Prithvi.
Yes.
Stay with the slides. Go back. 51, 50, yes. Yes, have you aware about the formula y is equal to FL cube by 8 EA? Have you already studied the subject strength of materials?
Not yet, sir.
Okay. If it is so, do you know the cantilever beam? I think in physics one.
Yes, sir. Mechanics of materials, I think last year we solved some similar problem.
Yes, this is the deflection formula for in the presentation itself you have given. Sailboat man.
Rod
Yes,
deflection.
yes, but it is the deflection formula for cantilever beam when it is subjected to UDL, uniformly distributed load. Then we can find the deflection at the free end using this formula, that is y is equal to f L power 4 by 8 EA. Okay,
Yes.
it was good. And go back still some more clarification. Go back to Chita's presentation. R, in one particular point, he's given the meaning for R. Yes, yes.
Slide, sir.
Yes. Yes, go back.
27, I think.
No, go back. Go back. Yes, 27. Yes, 27. Yes, here, Chita is what is mean by R?
Sir, the error, the difference.
Okay.
They
Any
have
other
denoted by R.
abbreviation for R? Why it is termed as R? Why it is not E?
No idea, sir.
It is
Yes.
a reminder term of the Taylor
Yes.
series.
No issue. No issue. This is termed as R because of residual. Residual. That is rest of the things. Which are the things which is not accumulated during calculation? That is rest. Left out. Residual. That is said to be in residual. Residual. The rest which we are didn't calculate it during our calculation, or it is an infeasibility for finding them during the calculation. That is what we are saying as error. That is called a residual. Yeah, in the subject finite element analysis, we have a technique to find the residual. Weighted residual method. There are 4 different techniques are available in order to find the residual. That is what we are going to learn in your finite element analysis. The technique which assists us to find the residual is weighted residual method. When we are having the hold with a residual, when we are having enough technique to find the values of the residual in a accurate way, then we can by that way we can increase our accuracy, solution accuracy, isn't it? That is why we are concerned about the error. When we are having the hold with the error, then we can increase the accuracy of our results. Okay, that's all. It was a very very good presentation by Chitash, Nirmal, Pradeep, and Prithvi. Who's handwriting? Chitash?
Sir, it's mine.
Yours.
Yes, sir.
In some places you are given where WHER only. Okay, that is a minor mistake, but in subsequent presentation, please have a conscious over the writings.
Okay,
Anyway,
sir.
my appreciations.
Thank you, sir.
Okay, and that's all about Unit 1. And I request all the representative to upload the PPT in our MS team. Then we can the other students can also have a visit over the PPTs during the examinations. And north side, in forthcoming Saturday we have which functions in uh, South India, and which function in North India? In Dasara, I think
Deepavali.
Dasara. I think you have Dasara in North India and Diwali in South India. Later, this Diwali be the happy and safe Diwali for everyone, and be safe. Yes, Sabrani, go ahead.
Sir,
Sabrani?
North also Diwali only, not Dashera.
Yes. Do you have any other functions parallel to Diwali?
Sir, like in West Bengal, we do Kali Puja and that's it. Like Diwali, Kali Puja.
Kali Puja. Dasara, that is during
So
Puja holidays.
Dashera is during Vijayadashmi.
Yes. Okay, fine. Take care. Take care during Monday. If it is feasible, we will meet Monday. Thank you. Thank you, Undal.
Thank you, sir.
Thank you, sir.